Welcome to this training session from Aerohive entitled Radio Frequency Measurements. In this session we will discuss absolute measurements, relative measurements, transmit versus receive amplitude, receive signal strength indicator thresholds, signal strength general rules, dynamic rate switching, signal to noise ratio, and coverage basics, hopefully answering a lot of questions you may have around these things. Absolute measurements. In Wi-Fi, absolute units of power measurement include watt and milliwatt and decibels measured, or dBms. Relative measurements in Wi-Fi include such things as decibels, decibels isotropic, and decibels dipole, used in discussions of receive power, gain, or loss. A relative measurement represents a change, not an absolute. It is just how the things have changed in power. As an RF signal moves from one point in space to another, it loses power due to at least free space path loss. A decibel is a relative measurement that is a unit of comparison as opposed to an absolute measure or a unit of power. For example, a 3 dB gain doubles absolute power, while a 3 dB loss reduces power by 1/2. An absolute measurement of power represents the transmit amplitude of a signal or the received amplitude of an RF signal. Examples of absolute units of power are milliwatts or watts, and decibels are referenced against 1 milliwatt. 0 dBm equals 1 milliwatt. As starting at a reference point of 1 milliwatt, 0 dBm would be the equivalent of no change. Transmit versus received amplitude. Transmit power includes the intentionally radiated power, how much energy you are purposely putting into an antenna prior to it going into the medium. The equivalent isotropically radiated power is exactly that, the power that is going into the medium. Receive power involves received signal strength indicator values. There is currently not a standard covering received signal strength value calculations. Received signal strength indicator values are calculated based on the individual chipset, and that calculation can vary from vendor to vendor. Receiver sensitivity plays a large role in this. Some receivers are more sensitive than others and can pick up even very faint signals down into the -97 or -98 dBm range, while other receivers are not quite so sensitive. There is really not a standard for calculating this, so two devices that are exactly the same distance from a transmitter could be receiving the same signal but indicating different values, just because they're using different chipsets from different manufacturers or from the same manufacturer running different versions of firmware developed at different times. The transmitter is the initial component in the system that actually puts the information in the air. This receives data from the system and begins RF communication. So when whatever application you're running decides I need to transmit this, that's what is going to put it into the air initially, or begin the process, is the transmitter. It's going to encode the data, it's going to modulate the alternating current signal, and it's going to send the modulated signal to the antenna to propagate into the medium. The receiver is the final component in wireless signaling. The receiver is the radio that takes the information out of the air. It converts the carrier signal into a series of ones and zeros, and the receive amplitude, or the receive strength, is always going to be weaker than the transmit amplitude. Notice the difference between the access point on the left transmitting at 15 dBm and the devices on the right receiving at -70 dBm. Why such a large disparity? It's because of free space path loss and initial signal loss upon transmission. The bulk of the power that is lost in RF transmissions is lost as soon as the signal leaves the antenna. It continues to weaken as it propagates away from the antenna. The farther away you are, the weaker the signal is going to be perceived. Most vendors implementing their chipsets to use higher data rates use a received amplitude of -70 dBm before their clients are able to access the higher data rates. Received signal strength can vary based on distance alone without any other source of interference. Notice the devices that are closer to the access point are receiving at a -53 dBm, and as we move farther away, -72 and -80. Very weak signals are unreliable for transmission because they are closer to a noise floor and may receive corrupted frames due to interference from non-802.11 sources of RF energy. The received signal strength indicator thresholds. Basic connectivity requires a signal strength of somewhere around -80 dBm coverage. High-speed connectivity, so that the clients can access the higher data rates provided by the manufacturers, requires around -70. Voice communications are recommended at -67 or -65 depending on specific vendors, and location tracking requires at least a -62 signal. When discussing voice, a -67 dBm signal is twice as strong as a -70 dBm signal, remembering that for every 3 dBm of gain you double the signal strength, and for every 3 dBm of loss you cut it in half. A -67 signal is 3 dBm stronger than a -67 signal. Since we're dealing with received signal strength indicator values, the receiving device calculates the value, not the transmitting device. Wireless signal strength general rules. A wireless client on a PC or a handheld device has a much weaker radio to transmit out than what you would find typically in an access point. A wireless client NIC on a PC or a wireless access point has a rated output of normally between 20 to 30 milliwatts up to around 100 milliwatts. 100 milliwatts equals 20 dBm. There is a rule in Wi-Fi called the rule of the tens and the threes. The general rules: a decrease in power or a loss of 3 dBm decreases the power by half, while an increase of power of 3 dBm doubles the power. When we're talking about the 10 of the tens and threes, a decrease in power of 10 dBm divides that power by 10, and an increase in power of 10 dBm multiplies the signal strength by 10. You can adjust your Aerohive access points using dBm. If you look to the right, you can see the adjustment here can be from 1 to 20 dBm, or you can leave it set to auto, and the Hive APs will negotiate their power as necessary for the RF environment. Relative versus absolute amplitude. A relative measurement represents change. What is changed here? What's different? As an RF signal moves from one point to another, there is going to be a change in that signal strength. It's much stronger near the transmitter and weaker as you get farther away. Remember, a decibel is a relative measurement that is a unit of comparison as opposed to a power unit. You may be transmitting at 20 dBm, which would be 100 milliwatts, but the receiver is receiving at a -70 dBm value. An absolute measurement of power represents the transmit amplitude of a signal or the received amplitude of a signal that is an actually measured value. Examples of absolute measure are milliwatts and watts. There are pieces of equipment that you can spin onto a radio or a cable that will measure the amount of power that is actually being intentionally pushed into the antenna. That's your intentionally radiated power, and that can be an absolute measurement. When you add the antenna into the mix and it is propagating into the air, then it's going to be a relative measurement as it propagates out to the client. Here is a simple rule of tens and threes. This is not intended to be an exact measurement. Let's suppose that you have a 14.5 dBi gain antenna. that doesn't divide evenly into tens or threes. You can actually use some mathematical formula to determine the true transmit power, but the rule of tens and threes will get you roughly to where you need to be to know if your signal is going to be legal or not for the given regulatory domain. Again, for every 10 dB of gain, you multiply your signal by 10. For every 10 dB of loss, you divide by 10. And for 3, if it's gain, you double. And if it's loss, you divide by 2. In this chart, you can see dBm and milliwatt conversions. 1 watt is equal to 30 dBm. In some regions, transmitting at that signal strength is illegal. In North America, 1 watt is the maximum allowed power for your intentionally radiated power, and the maximum equivalent isotropically radiated power, the EIRP, varies based on the type of connection. If you're using a point-to-multipoint scenario, which simply means you're using an omnidirectional antenna, you're limited to 4 watts in both 2.4 and 5 gigahertz. If you're using a point-to-point connection in 2.4, you're still limited to 4 watts of maximum EIRP. However, if you're using Uni 3, the upper uniband, and it is a point-to-point connection using highly directional antennas such as a dish or maybe even a Yagi, so it is not an omnidirectional connection, you may be allowed to use a couple hundred watts or more. The signal strength that we want to talk about for our comparison here would be signal strengths relative to what the client is going to see the transmitted power out. If you're seeing anything stronger than a neg 50, that is a very, very strong signal. You're very close to the transmitter. Anything down to neg 70 is still considered to be a very good signal because at negative 70 dBm, most client manufacturers will allow you access to the higher data rates. Weaker than negative 80, you start getting into a do not care area. If there's RF energy here and I can use it for signaling, that's okay, but that is not my intended area of coverage. When you get down to negative 90, negative 95, you're reaching the noise floor, the area where you have interference from different pieces of equipment such as fluorescent lights, microwaves, at distance, the sun, anything that creates any RF energy at all in that low receive signal strength will more than likely disrupt your connectivity to the access point. Anything weaker than negative 95 is considered to be an unusable signal strength whatsoever. Dynamic rate switching. As clients move farther away from the access point, in order to stay connected, they will lower their data rate as they move farther and farther away. In addition to lowering the data rates, they might change their modulation and coding schemes. You could have an 802.11g capable access point and an 802.11g capable client connected, but as the G client moves farther away from the access point, it will drop into the high rate direct sequence spread spectrum data rates and change modulation techniques, kicking off a protection mode in the service set. Interference and signal to noise ratio. The closer you are to the transmitter, the stronger your signal is going to be, the better the quality of your transmissions. The farther away you move, the weaker that signal is going to be, and you're going to get closer to the noise floor. Hence the name signal to noise ratio. Based on the signal to noise ratio, the client and access point are able to negotiate a data rate in which to send their packets. So the higher the signal to noise ratio, the better. For good performance, the signal to noise ratio should be greater than 20 dB. For optimal performance, the signal to noise ratio should be at least 25 dB. Coverage basics. There are environmental considerations for configuring your networks, square footage considerations, the applications being used, the particular client devices, security mechanisms in use, channel planning, and site surveys to be conducted. Site survey basics. Spectrum analysis, coverage analysis, and AP placement and configuration and application analysis. Spectrum analysis examines layer 1 of the OSI model, just particularly looking for anything that could be out there as noise, not specifically looking for anything that is modulating 802.11 signals, but looking for anything that may interfere with those signals because it is making noise in the same frequency range. Oftentimes, surveys do not conduct spectrum analysis, resulting in a poorly done survey and clients that have to deal with noise consistently rather than having a clean environment, simply because the surveyor neglected to do a layer 1 analysis and stuck strictly with a layer 2 analysis, looking only for other 802.11 devices in the same space and not thinking about the non-802.11 devices that are creating noise that the clients must also contend with for the medium. Spectrum analysis is truly the layer 1 diagnostics. This is going to reveal devices for you that are not just contending at layer 2, but are transmitting and making noise at layer 1. When an 802.11 device does a clear channel assessment, it's only looking for devices that are on the same frequency and modulating data, not looking for noise sources such as microwaves and cordless phones. Spectrum analyzers are frequency domain measurement devices that can measure amplitude and frequency space of electromagnetic signals. Spectrum analysis hardware can cost over $40,000 US or more depending on the type you use. You can also acquire some that are simple USB devices that plug into your laptop and are only around $500. So depending on how much of this work you're going to do and the amount of detail you need, there's a plethora of devices out there that should cover exactly what you need to do for this. To conduct a proper 802.11 spectrum analysis survey, the spectrum analyzer will need to be capable of scanning both the 2.4 GHz ISM band and the 5 GHz unibands. Aerohive includes, at no additional cost, spectrum analysis with the Hive APs. The Hive APs can use their 802.11 radios to do some limited layer 1 analysis, providing a chart such as the one you see in this slide. Coverage analysis may require a manual site survey. You may have to go out and listen to see how far the APs are able to transmit at the data rates prescribed versus all the noise that's in the airspace. You'll need to document any existing 802.11 devices because any clients or devices you deploy are now going to have to contend for that airspace on those frequencies. Knowing where these neighboring devices reside will allow you to better place your access points on different frequencies to avoid creating more co-channel interference or co-channel cooperation. Documentation of existing networks is a requirement for a proper site survey. Expected client use should also be taken into account. Just because your laptop has great signaling and can do what it needs to do, maybe running iPerf or something like that, does not necessarily mean that the voice over Wi-Fi handsets are going to work properly or the barcode scanners you're using are going to work properly for that. So when you're conducting a coverage analysis, you can do this with the devices that are going to be deployed in that airspace to make sure that you're really getting what the client devices need. Remember, site surveys and deploying Wi-Fi are not about what the access points can do, but they're about the environment in which the clients operate and what the clients require in order to operate in that environment. Post-deployment validation is also part of a properly installed network and the survey process. When you're doing the survey, you may use predictive survey software, you may do a walkthrough, but at the end of the deployment, you absolutely need to do a post-deployment validation because things could have changed since you deployed or since you had done your survey. You need to also verify that the devices are working as expected within that airspace. Access point placement is another key part of deciding where to work with your networking. If you're using an access point such as the one pictured here, you're going to need to make sure that you place it so that the front of the access point is actually facing towards the client. Oftentimes I've seen internal antenna access points like this in the ceiling tile laying face up, which provides great coverage for the air conditioning system, but provides no coverage where the clients reside. Beyond simply identifying areas of RF coverage and RF interference, a good site survey will also determine the best locations for wireless devices. The proper placement of wireless devices is very important. Connectivity to the distribution system, which is the wired network, as well as power for the wireless devices must also be considered. The distance cables need to run for the connection to the access point is also important, especially if you're going to be using power over Ethernet, because you're going to need to reduce those cable runs to compensate for the PoE usage. Application analysis. You're going to want to conduct some throughput testing to make sure that the applications are working as desired on the client devices. You're also going to need to look at the data rates required by those applications to make sure those are being met. Any client device functionality that your users are depending on to do their jobs, you should test that as well. Maybe solicit some of the users to get some of their interaction, some of their ideas about is it working properly or not, is it as fast as they expected or as fast as they need to service themselves and maybe their customers. And then a post-deployment validation could be done immediately after the deployment, but you may also want to do one after the users are actually up and on the system, analyzing what a full load is doing on the system with all of the users supported during the day. Site surveys using predictive modeling can be done, and Aerohive does include topology mapping along with the product, again at no additional charge. If you are not yet an Aerohive customer, you have the ability to use our planning tool online at no charge. Simply register and you will have access to the planning tool. Predictive site survey tools use the known attenuative values of partition types such as drywall, concrete, elevator shafts, bricks, glass, the things that you're typically going to find in buildings, to determine where to place the access points and how many to use. You can see the modeling here has added multiple access points, and the requirements for this is application for voice, signal strength of -67 dBm. So everywhere you see blue coloring here, that is at least a -67 dBm signal strength, and the signal will be getting stronger as you move towards the access points. You can plan for data, you can plan for voice, you can plan for background. It all varies based upon the client needs and the particular environment. As you start seeing holes in the coverage, you'll be able to move the access points around on the map to provide coverage in those holes or add more access points as necessary. By using a predictive modeling survey, you are going to save hours of walking around taking manual readings of what the physical environment would let you do. Although you've done a great job with the predictive modeling does not take into account noise, so you're always going to need to pair the predictive modeling, which takes into account the free space path laws, the transmit power and types of access points you're using, and the partitions in between the client and the AP, but it doesn't take into account the noise that's actually in the airspace. You may simply do a spectrum analysis in the airspace, or you may do both a layer 2 and layer 1 analysis in the airspace and adjust your modeling as required. You can render a deliverable out of this, a PDF version, and hand it to potential installers and tell them, put APs on the map where I've indicated here, and you'll have the devices hung exactly where your predictive modeling has indicated. To use the online planner tool at no charge, you can go to www.aerohive.com/planner. Then there'll be a registration form, and you can use this at no charge whether you are an Aerohive customer or not. If you are an Aerohive customer, you can simply access the topology maps inside your Hive Manager. Thank you for viewing this session on RF, from measurements to values for site surveys from Aerohive. Please continue the rest of the series at your earliest convenience. Welcome to this training session from Aerohive on radio frequency fundamentals. In this session, we're going to cover what exactly is an RF signal, RF propagation behaviors, spread spectrum technologies, and hopefully answer a lot of questions you may have about how RF signals actually propagate. What is an RF signal? An RF signal actually starts out as an electrical alternating current. It's a signal that is originally generated by a transmitter. This particular signal is then radiated out of an antenna element in the form of an electromagnetic wave. An RF signal is an alternating current that continuously changes between a positive and negative voltage, which can be represented as a sine wave. Any type of cycle or oscillation of this alternating current is defined as a single change from up to down, or as a change from positive to negative to positive. RF signals are defined by various characteristics including wavelength, frequency, amplitude, and phase. Phase, frequency, and amplitude shifts can all be used by transmitting radios to actually modulate data. You may be familiar with amplitude modulation and frequency modulation from standard civilian radio stations. Wavelength. Wavelength is the distance between two successive crests or peaks or two successive troughs or valleys of a wave pattern. As you can see in this slide, you can see the distance measured between two peaks. You could just as easily have measured between two troughs. In simpler terms, a wavelength is the distance that a single cycle of an RF signal actually travels. Frequency is the number of times per second that a signal oscillates. It's the number of times in a specified event occurring within a specified time interval, in our case per second, the number of times that the signal oscillates. The standard measurement for frequencies is in hertz. The event that occurs once in a second is equal to 1 hertz. An event that occurs 2.4 billion times in a second is measured as 2.4 gigahertz. The frequency at which an electromagnetic wave cycle is also measured in hertz. The number of times an RF signal cycles in 1 second is the frequency of that signal. So the higher the frequency, the more oscillations occur within that same time period, and the shorter the wavelength is. The larger the frequency, the smaller the wavelength is going to be. The lower the frequency, the larger the wavelength is going to be. And that is illustrated by the inverse relationship between frequency and wavelength. Frequency is equal to the speed of light divided by the wavelength, and the wavelength is equal to the speed of light divided by the frequency. Therefore, they have an inverse relationship. The greater the frequency, the smaller the wavelength. The lower the frequency, the larger the wavelength. Phase. Signals can be either in phase with each other or out of phase with each other, and there can be varying degrees of being out of phase with the main signal. A signal that arrives in phase at the same time with the main beam signal will create upfade. Signals that arrive out of phase with each other will create downfade and result in reduced throughput. This can be caused by reflections or refractions of signals that are not quite arriving the way expected at the intended receiver. If a signal is 180 degrees out of phase and arrives at the same time as an in-phase signal, the two signals cancel each other out. This phenomenon is called nulling. Amplitude. Amplitude is simply a strength of the signal. It can be characterized as signal strength or power. When discussing a signal strength in a wireless LAN, amplitude is normally referred to as either transmit amplitude or receive amplitude, which would be transmit or receive strength. Transmit amplitude is typically defined as the amount of initial power that leaves the transmitter. For example, if you configure an access point to transmit at 10 milliwatts, that is the transmit amplitude. If you configure it to transmit at 100 milliwatts, that is the transmit amplitude. Antennas are then added to the system And antennas are bidirectional passive amplifiers. So the antennas will amplify the original transmit amplitude. When a radio receives an RF signal, the received signal is also going to be given some receive amplitude increase due to the antenna's bidirectional passive nature. All RF signals lose amplitude or strength as they propagate. This phenomenon is called free space path loss. The farther the signal travels, the weaker it's going to get. Signals in RF lose their majority of strength as soon as they leave the antenna and continue to lose strength as they get farther and farther away. For that reason, to get the higher data rates, a client needs to be closer to the transmitter. RF propagation behaviors include such things as absorption, reflection, scattering, refraction, loss, free space path loss, multipath, whether it's good or bad for the intended signaling, and gain. If you think of waves propagating through the air, such as light and sound, and relate the same things that could affect what light and sound go through to what RF signals go through, that'll make understanding this quite a bit easier. Absorption is when the signal strikes an object and is not allowed to pass through that object, nor is it reflected by the object. It is considered to be absorbed, or it stops inside the object. Some absorption exists even if the signal is allowed to propagate through objects. Many of these things exist in some degree. Reflection and absorption are always there, but they may not be at a 100% level. Reflection is when a signal strikes an object and is not absorbed by it, nor is it allowed to pass through the object, but it rather bounces off, just like sound bouncing off a wall or light reflecting off of something. Refraction. Refraction is when the signal is changed in direction due to passing through a different type of medium. A good definition of this is the bending of a signal as it passes through a medium with a different density, causing a redirection of the wave to change. The RF refraction most commonly occurs as a result of some atmospheric condition. The three most common causes of refraction are water vapor, changes in air temperature, and changes in air pressure. An indoor environment is less likely to suffer from refraction due to being in a controlled climate. Outdoor environments are going to be the ones that normally suffer from this more because the RF signals typically refract slightly back down towards the Earth's surface. However, changes in the atmosphere may cause the signal to bend away from the Earth, and long-distance outdoor wireless bridges, refraction can be an issue. An RF signal may also refract through certain types of glass and other materials that are found in an indoor environment. Diffraction is the bending of an RF signal as it wraps around an object. As you see in the diagram here, there are shadows behind these buildings with the sun on the opposite side. The light bends around the building. Just as there are shadows for light, there are also RF shadows. When conducting a site survey or deploying a network, you want to make certain that any RF shadows that exist are not in areas where clients or other devices are expected to be deployed. Scattering. Scattering is kind of like multipath on steroids or reflection on steroids. Some uneven surfaces, such as choppy water, the tops of multiple vehicles in a parking arrangement, can cause scattering. Actually, the color blue of the sky is caused because of scattering. The wavelength of light is smaller than the molecules in the atmosphere, so when the light hits these molecules, it is going to bend. It's known as Rayleigh scattering. The shorter blue wavelength light is absorbed by the gases in the atmosphere and is radiated in all directions, causing the blue sky effect. Just as light can be scattered, so can RF signals, since they are both in basic form a wave passing through the atmosphere. Multipath is when a signal takes more than one path to arrive at the intended receiver. Multipath is a propagation phenomenon that results in two or more paths of a signal arriving at a received antenna either at the same time or within nanoseconds of each other out of phase. If they are arriving at the same time, that can create upfade. Arriving off from each other can create downfade and reduce throughput. Multipath you may have actually heard before. Not heard of, but heard. Multipath in RF is very much like an echo for sound. Delay spread. The delay spread is the time difference between the main signals arriving and any reflected signal arriving. This can cause problems for devices that are using single input, single output. Multipath creates a problem for those devices and is usually mitigated by using what is called antenna diversity. Multiple antennae connected to the same radio. But unlike 802.11n's use of MIMO, CISO devices strictly use this for diversity. Whichever antenna receives a stronger signal, that signal will be believed, the other signal will be discarded. The signal usually arrives via multiple paths and with different angles of arrival. The time difference between the arrival moment of the first multipath component, which is normally the line of sight component, and the last one is called the delay spread. This difference is going to cause a problem for the radios. The delay spread time differential can cause bits to overlap with each other and the end result being corrupted data. This is known as inter-symbol interference. By default, 802.11 radios have an 800 nanosecond tolerance for the delay spread, which is known as the guard interval. Newer technologies may use shorter guard intervals. Gain or amplification. Gain is when a signal is made stronger. Gain can be either passive or active gain. Passive gain is accomplished by focusing the RF signal with the use of an antenna. Again, antenna being bidirectional passive amplifiers. There is no additional current or anything added into the signal, but rather the focusing of the beam due to the elements inside the antenna. Active gain is caused by the addition of an amplifier onto the wire that connects the transceiver or the radio to the antenna. The amplifier is usually bidirectional, meaning that it increases the AC voltage for both inbound and outbound traffic. Active gain devices require the use of an external power source, whereas antennae are passive and do not require such a power addition. Loss or attenuation. Loss exists in every transmission. There's going to be some loss due to free space path loss as the signal propagates, but there may also be loss due to impedance mismatch of connectors, length of cable run between the transmitting radio and the antenna, or any environmental factors that may affect the propagation of the signal. Free space path loss occurs in every signal, even between laptops using an ad hoc network on the same table, although that degree of free space path loss would be minimal. Free space path loss is the loss in signal strength or reduction in amplitude of a wave that would result from a line of sight path through free space, meaning there are no obstacles causing reflection, absorption, diffraction, or other things that you would find having problems. This is what you would expect to see on a bounded network through cables. Once a signal leaves the system, it's going to lose the bulk of its energy. Much like a projectile leaving a barrel, that's where it loses most of its energy. The signal will lose most of its energy as it leaves the antenna. A signal will continue to travel, but with less strength, and at some point you might actually be able to pick up some RF energy, but you're probably not going to be able to use a reliable 802.11 signal due to distance from the transmitter and free space path loss. Spread spectrum technologies. We will discuss in this section modulation encoding, high rate direct sequence spread spectrum, and orthogonal frequency division multiplexing. Modulation. Modulation is the process of varying one or more properties of a high frequency periodic waveform called the carrier signal with a modulating signal which typically contains information to be transmitted. WLAN radio cards use different types of modulation methods to represent data bits as they are delivered via an RF signal. OFDM uses binary phase shift keying and quadrature phase shift keying. Phase modulation for the lower OFDM data rates is used. The higher OFDM data rates uses 16 QAM and 64 QAM modulation. QAM meaning quadrature amplitude modulation. It's a hybrid of phase and amplitude modulation. Modulation and coding schemes. Again, modulation is a process of varying one or more properties of a high-frequency periodic waveform called the carrier with a modulating signal which typically contains information to be transmitted. Coding varies based on the type of modulation being used. There's a chart here you can see which is really beyond the scope of this training, but you can tell from the different speeds and the different modulation techniques that different standards and different devices are going to require the communications to match in order to get the same speeds. Why are they important? If they don't match, then the devices cannot talk. High rate direct sequence spread spectrum, or 802.11b, if you remember from an earlier session, uses different techniques to get us into the 5.5 and 11 megabit data rate than were used by the Barker coding at 1 and 2 megabits. 802.11b, or high rate direct sequence spread spectrum, uses complementary code keying, CCK, at 5.5 and 11 megabit data rates, and it is used by 2.4 gigahertz range devices using 802.11b. High rate direct sequence spread spectrum also uses two modulation techniques: differential binary phase shift keying and differential quadrature phase shift keying to get different data rates. Barker coding and CCK coding are the two encoding methods used by 802.11b. Orthogonal frequency division multiplexing, or OFDM, uses 52 subcarriers per channel and is used by 802.11a, 802.11g, and 802.11n. And you will find it using 802.11n in both the 2.4 and 5 gigahertz bands, whereas A is just 5 gigahertz and G is just 2.4. The 802.11 standard, as amended in 2007, specifies the use of OFDM at 5 gigahertz and also specifies the use of extended rate physical OFDM at 2.4 for G. OFDM and ERP OFDM are exactly the same technology. The extended rate physical component comes in because the rates of OFDM were extended into the physical space of 2.4 gigahertz for G to be used. OFDM is often referred to as a spread spectrum technology because of similarities with how spread spectrum technologies work, even though that is not accurate. OFDM actually transmits across 52 separate, closely and precisely spaced frequencies, which are often referred to as subcarriers. Thank you for watching this session from Aerohive covering radio frequency behaviors and propagation. Welcome to this training session from Aerohive covering an overview of wireless standards, organizations, and fundamentals. In this session, we are going to discuss the IEEE, the Wi-Fi Alliance, the Open System Interconnection Model, and Wi-Fi, where they fit together, RF bands used by current Wi-Fi devices, some basic site survey discussions and deployment considerations, which should answer quite a few questions people normally have about these topics. The 802.11 standard and all of its amendments are brought forth by the IEEE. The IEEE is the Institute of Electrical and Electronics Engineers, which sets forth all of the requirements that we follow for 802.11 use. The original 802.11 standard was developed in 1997. It defined direct sequence spread spectrum, frequency hopping spread spectrum for use within the 2.4 gigahertz band, allowing for 1 and 2 megabit data rates. Since that time, the 802.11 standard has been ratified and changed to allow the industry to move and grow into new technologies as the equipment becomes available or as the technology demands such growth. For a complete understanding of the IEEE and 802.11, you can go to standards.ieee.org. The major amendments under which we operate in wireless LAN configurations are as follows. For modulation and data rate, 802.11a, b, g, and n were developed. 802.11a and b were ratified in 1999. 802.11b was an enhancement over the original 802.11, which allowed high rate direct sequence spread spectrum as well as backwards compatibility with legacy 802.11. 802.11a introduced data rates of up to 54 megabits and a new modulation technique to Wi-Fi called orthogonal frequency division multiplexing. OFDM and the data rates used by A were much faster than those used by 802.11 and 802.11b, but they worked in a different frequency range. 802.11a operates in the 5 gigahertz range. Seeing the speeds that A offered, people wanted those speeds in 2.4, but we had to have backwards compatibility with existing 802.11b and 802.11 devices. 802.11g was ratified for that purpose. 802.11g uses extended rate physical OFDM because it extends the rates of OFDM into the physical space of 2.4. It also has backwards compatibility methods to work with legacy devices and protection mechanisms in the event that there are non-members using legacy technology in the surrounding airspace. 802.11n was a brand new way of approaching how we modulate. It allows us to use high throughput OFDM. It allows us to use aggregate MMPDUs, which is really a block data frame, block acknowledgments, channel bonding. It also allows or introduces for mandatory use multiple input and multiple output radio systems. So there are several reasons that 802.11n is faster, so many so that there is a separate learning opportunity just on 802.11n in this series. The security that was initially offered under the 802.11 standard of 1997 was very lacking. In 1999, the IEEE introduced WEP, Wired Equivalent Privacy. Wired Equivalent Privacy allowed us to have some degree of security, but was quickly found to be very weak. While the IEEE was working on adding more security in, they did not want to rush something else out, so it was a few years before 802.11i was introduced, which is the major security amendment, introducing multiple new authentication and encryption techniques, making wireless more secure and actually more adoptable in areas that had refused to use the more insecure WEP or wireless in general for years. 802.11w has also been ratified, which introduces protected management frames. Protected management frames are intended to stop denial of service attacks, which simply use spoofed deauthentication and disassociation frames. The client and the access point are required to mutually authenticate prior to accepting any such frame. As we developed more friendly devices, we started using voice over Wi-Fi and handset devices that wanted to be wireless so we could be untethered and move about. Unfortunately, clients control how and when they roam, and there was not really a roaming standard. 802.11f was a recommended practice, but even if we could roam between access points, you would still maybe cross a layer 3 boundary, having some difficulties there. 802.11r is a roaming standard, but you still see several vendors producing devices, client devices, that roam in the legacy manner in which they've roamed for years, because they don't want to retool how they make things. 802.11k also allowed for partial faster roaming with more security. Since we've moved into devices with voice and video using Wi-Fi, there had to be some type of quality of service amendment, and that is 802.11e. 802.11e introduced block acknowledgments and transmit opportunities, When a device wins a contention for the medium, rather than simply being able to transmit one frame, that device is given a transmit opportunity, during which time it can transmit multiple frames when it wins a contention. That way you have a much faster delivery of voice and video, which are more time dependent and more sensitive to disruption in the medium. The amendments and data rates. 802.11, the original or legacy standard, supported data rates of 1 and 2 megabits within the 2.4 gigahertz spectrum. It used direct sequence spread spectrum or frequency hopping spread spectrum and single input, single output or SISO radios. 802.11b enhanced that and is called high rate direct sequence spread spectrum, still working in 2.4 gigahertz, but introducing the data rates of 5.5 and 11 megabits. I know that by today's standards, 5.5 and 11 megabits are not deemed to be high rates, but when you compare them to the 1 and 2 megabits offered by legacy 802.11, they were several times faster. 802.11a operates in 5 gigahertz. It promises data rates of up to 54 megabits per second, and it uses orthogonal frequency division multiplexing, or OFDM. Like 802.11b and 802.11, 802.11a also uses single input, single output, or SISO radios. 802.11g being introduced to provide higher data rates up to 54 megabits in the 2.4 gigahertz spectrum also uses orthogonal frequency division multiplexing. It uses extended rate OFDM, ERP OFDM, which allows G to operate in the same airspace as legacy B devices because it has some protection modes built in to operate within the airspace with neighbors and allow legacy clients to still operate within the same service set. 802.11n operates in both frequencies, 2.4 and 5 gigahertz. It also has protection modes built in for non-members and for mixed mode environments with legacy clients, and it promises data rates of up to 600 megabits per second. It uses high throughput OFDM, and it uses multiple input, multiple output radio chains. It also uses channel bonding, aggregate MMPDUs, and block acknowledgments. There are several reasons that 802.11n is faster. It also uses transmit beamforming and also has the opportunity for transmit beam steering. There are many reasons that 802.11n is faster, and it is so different than the other technologies that it is worthy of its own separate discussion, which comes in a later session. The Wi-Fi Alliance. The IEEE introduces the standards. Vendors work within those standards, but there's a lot of wiggle room, and still being following the standard, your devices may not have worked with someone else's devices. Back in the early days of Wi-Fi, many companies were making client radios that would only work with their brand of access points. That created a lot of problems as the smaller companies either went out of business or were bought by larger companies who shut off that part of the market. You were then forced to replace all of your infrastructure or run multiple infrastructure types that would not interoperate. The Wi-Fi Alliance came about to provide highly effective collaboration so that the vendors can work together to make sure that one vendor's client will work with every vendor's access point and vice versa. The Wi-Fi Alliance tests extensively all of the products and will give them the Wi-Fi certified logo to use if the devices meet that spec. Before 802.11i was ratified, the Wi-Fi Alliance, in addition to making sure that everyone worked together, helped to usher in security into Wi-Fi by telling the vendors that they needed to write to this new Wi-Fi Protected Access, or WPA, standard if they wanted to continue getting their Wi-Fi certified stickers. That means that if you don't comply with that, you wouldn't be able to sell into a market that wanted compatibility. So vendors rushed quickly to make that happen, writing new firmware updates and creating new devices that comply with WPA. Prior to 802.11i's final ratification, the Wi-Fi Alliance released 802.11 compatible WPA2, which was pretty much a snapshot of how the IEEE had envisioned 802.11i to work, helping the community not only work more efficiently together and collaborate, but also making Wi-Fi more secure. The Wi-Fi Alliance has done a great job in fostering the growth of wireless LANs across the world. For more information about the Wi-Fi Alliance, you can go to www.wi-fi.org. The relationship between the Open System Interconnection model and Wi-Fi. The OSI model has 7 layers, starting at the top with application. Then we have presentation. At the presentation layer, you'll see things like encryption and formatting. Then you have the session layer, we have the transport layer, we have the network layer, which is where we get our IP addressing, and it's responsible for routing of packets. But all of those layers are layers at which Wi-Fi does not work. Wi-Fi encapsulates those layers in its payload in the frames, but only uses layers 1 and 2. Layer 2, the data link layer, and layer 1, the physical layer, are the 2 places in which Wi-Fi actually operates. Layer 1, the physical layer, is the medium. The medium in this case being the air largely, and I know there are RF cables out there, and it's still an RF signal inside that cable, but normally when you think of Wi-Fi, we think of being in the air. The medium being the air leaves the transmissions vulnerable to noise more so than a wired network. Wired networks are susceptible to electromagnetic interference, but not nearly to the degree that an unbounded network of a WLAN would be. 802.3 Ethernet definitely uses cables, but 802.11, the RF medium is the air. So not only are you more susceptible to noise, you're more susceptible to eavesdropping, and it's a larger contention domain. All the radios in the same basic service set area on the same frequency can hear each other and will cooperate, much like devices plugged into the same hub, but instead of using collision detection, we're using collision avoidance in Wi-Fi, and that's why it's important to make sure that you channel allocate properly to avoid those problems. Most discussions of the OSI model only lead you to believe that the data link layer has sublayers. However, all the layers have sublayers. The 2 sublayers for the physical layer are the physical layer convergence protocol and the physical media dependent sublayer. The physical layer convergence protocol is responsible for taking information from layer 2 and preparing it to go to the PMD out into the medium, taking things that the PMD has pulled in from the air and preparing those to go up to layer 2. The physical media dependent sublayer is the sublayer that actually places data in the medium and takes things from the medium. It is also in a wireless environment where the clear channel assessment occurs. Layer 2, the layer at which we normally are taught about sublayers, has 2 sublayers. The media access control sublayer, which manages access to the physical medium and handing things down to the physical layer convergence protocol at layer 1, and the logical link control sublayer, which manages the flow of multiple simultaneous network protocols over the same network medium. Devices operating no higher than layer 2 include things like network interface cards, layer 2 Ethernet switches, bridges, and access points. Access points work as multiple different devices. In this discussion, they are more hub-like. They're also not going to have the ability to make switching happen because you can't switch a wireless signal in the air. When you look at the diagram, you can see that there is a MAC header. We have the frame body, which is the MSDU, and we have the frame check sequence, which is where we have the cyclical redundancy check. Everything inside the frame body has the potential of being encrypted using several different types of encryption as laid out by 802.11i. The MAC header and the trailer are never encrypted. They have to be in clear text in order for the devices to know how to communicate with each other, even on a wired network. The MAC header includes things like the source address of the frame, the transmitter address, which is the radio that actually put the frame in the air, the receiver address, the radio that should be receiving that frame, and the ultimate destination address. So you can quickly map out someone's network just by watching the frame exchanges. Inside the header, you'll also find the type of frame it is, whether it's management, control, or data, and the subtype of frame. You're going to also see the type of encryption used and a timestamp and any vendor-specific information. There's a lot of valuable information in that header. The standard size of a wired frame, you may have seen it as MTUs. The The standard size there is normally 1500. You can see that the wireless frame can be much larger because it has to encapsulate all of the things from layer 3 and up, plus have enough valuable information for layer 2 so that the devices can work together and contend for the medium properly. Radio frequency bands used in Wi-Fi. We have the 2.4 gigahertz ISM band, and we have the 5 gigahertz uni bands. And inside that, there are frequencies that are reserved or set aside as specific channels based on the space that they use within the given band. The 2.4 gigahertz band is 83 megahertz wide. There are 14 channels available within 2.4 gigahertz, although not all channels are legal in all regions. Each channel will be either 22 megahertz wide if you're using direct sequence spread spectrum or frequency hopping spread spectrum, and 20 megahertz wide if you're using orthogonal frequency division multiplexing or OFDM. Various non-802.11 devices also work in this frequency range as well as in 5 gigahertz, but the majority of devices causing problems for 802.11 that are non-802.11 devices are found in 2.4. Such devices include microwave ovens, baby monitors, X10 cameras, Bluetooth, and walkie-talkies. Very common devices to find around an office space. So there's a lot of noise there. What that means is when the devices do their clear channel assessment, they're looking for 802.11 transmissions with which they need to contend for the medium or back off and let those devices finish their communication before they start. When they perform their clear channel assessment and hear one of these non-802.11 sources of interference, they assume that the medium is idle, will transmit and collide with that noise, causing a high retransmission rate and a great reduction in throughput. Up to about a 5 or 10% retransmission rate may be deemed normal for certain networks, but even still, that is a retransmission and the throughput will be lower because of transmitting the same frames multiple times. The channels used in 2.4 overlap with each other. If you have 14 channels that are either 20 or 22 megahertz wide and you only have 83 megahertz of space in which to use them, obviously there will be some overlap. Channel 1's center frequency is 2.412. That way, if you're using spread spectrum technologies and you're using a 22 megahertz wide channel, if you split it in the middle right off of 2412, you'll see that you go down 11 and up 11 from there, and I'll take you to 2.401 as you go down towards the bottom, keeping you within the legally allowed non-licensed frequency range. When you go up for the other 11, it'll take you to 2.423, which unfortunately is the center frequency for channel 3. So you'll see there is some overlap from channel 1 all the way up through channel 3 just with what channel 1's causing on its own. If you'll notice channel 5's center frequency is going to be on 2.432, and it's going to go down 11, taking it to 2.421, and that is within the same range that channel 1 is overlapping into channel 3. So channel 1 overlaps all the way up through channel 5 with the sidebands from the other channels coming down and channel 1 going up. Channels 1 and 6 are considered to be non-overlapping adjacent channels because their center frequencies are 25 megahertz apart. Being 25 megahertz apart allows each channel to be 22 megahertz wide, channel 1 going up 11, channel 6 coming down 11 without any overlap. Again, channel 1's far sideband moving up will be 2.423, channel 6's sideband moving down will be 2.426. So if you're using direct sequence spread spectrum, there is a 3 megahertz separation between the channels. If you were using OFDM, that separation would move up to 5 megahertz because each channel would only be 20 megahertz wide. The next channel in which this phenomenon occurs is channel 11. So you can see quickly why channels 1, 6, and 11 are more often used than other channels. It allows us to co-locate 3 devices without reusing channels at all, breaking up the contention domains properly. If you were using all 14 channels, you would still only be able to co-locate successfully 3 access points in the same physical space without reusing a channel. So it really doesn't matter if the government where you live has restricted you to only 1 through 11. You're still only going to be able to successfully co-locate 3 APs anyway. If you are in countries that allow channels 12, 13, and 14, you may wish to use just 1 through 11 anyway to provide good connectivity for all of your users, plus any people who are traveling with devices that may not be able to use the frequencies of channels 12, 13, and 14. This illustration shows us a proper channel reuse pattern using just channels 1, 6, and 11. You'll see that no cells overlap using the same channel. If you're looking on the far left-hand side, you'll see 2 cells both using channel 6, but upon closer inspection, you'll see that the cells do not overlap and the APs would not hear each other, so therefore you are still in separate contention domains even though you are fairly close to each other. That's because indoors you normally turn the power level down on the access points to allow more APs to be deployed to break up the collision domain so you have fewer clients contending for the airspace at the same time, thus improving throughput. This illustration shows us an adjacent channel interference with the cells where we're seeing channels that overlap with each other deployed on APs in the same physical space that can hear each other. When an AP in this scenario conducts its own clear channel assessment, it may not hear the other access point and be able to discern that it's an actual 802.11 signal. It may hear it, determine its noise because they're not on the same frequency and they don't overlap enough in their sidebands to really decode the frames. They'll assume it's noise, and when the devices transmit, they will collide with each other, again forcing a high retransmission rate and reducing throughput greatly. This is a very poor design. Co-channel interference is the traditional term given when access points are on the same channel and in the same space. It's not very accurate, though, to call it interference. It's more similar to an extended collision domain, making it larger, so we'll call it co-channel cooperation. All of the APs on the same channel that hear each other will contend for the medium properly. However, it's easily seen why it's called interference, because when you have multiple devices contending for the same airspace at the same time, you're going to have to back off more, and it's going to slow down your network almost as much as having a lot of collisions from a non-802.11 source of interference. There is a very niche deployment called single channel architecture using controllers. The APs only transmit when the controller allows it, and the controller is supposed to make sure that no 2 APs that can hear each other are able to transmit at the same time. This reduces service to your clients and reduces overall throughput for your network, and much like a channel plan using all the channels with co-channel overlap, this is going to be a very poor design. You don't want to do this in an environment where you're really worried about quality of service for your devices. This is not a good plan. The 5 GHz band is broken up into 3 major sections: Uni 1, Uni 2, and Uni 3. There is also a second Uni 2 opportunity called Uni 2 Extended. OFDM channels work in the Uni bands and were extended down into the ISM bands in 2.4 with 802.11g and 802.11n. In 5 GHz, all of the channels are 20 MHz wide, and in this range there are 23 non-overlapping channels. So in theory, you could co-locate as many as 23 access points without having to reuse the same channel once. Uni 1 has 4 channels, as does Uni 2 and Uni 3. Uni 2 Extended has 11 more channels, bringing us to the total of 23. The problem here is that there are not very many client devices that work inside Uni 2 and Uni 2 Extended. So the majority of the 5 GHz band clients are going to be found in Uni 1 and Uni 3, limiting you to 8 channels. Some countries have been using Uni 2 for quite some time, and you may have some clients there that can work in all of the bands without any problem. Other organizations have decided, no, we're not going to allow that, so you're only allowed in Uni 1 or Uni 3. Again, that's going to depend on your locale and the governing body for that region. If you are working in Uni 2 and Uni 2 Extended, some regions require you to use what are called Dynamic Frequency Selection Devices, or DFS. These devices will have the access points periodically go off channel, scan for channels where there is no noise, save that, and then if there's suddenly noise or interference on their own channel, we'll send out a special management frame called an action frame to the service set. The entire service set would then change channel all at once without the hassle of having to re-authenticate and reassociate. It sounds great in theory, but in practice you actually wind up orphaning some clients. The reason that is a requirement is because of weather radar that works in that same frequency range, and we do not want 802.11 to interfere with the radar. The 5 GHz channels, as you see, start with channel 36 and go up in increments of 4. So in Uni 1 you would have 36, 40, 44, and 48, and then into Uni 2 you would have 52, 56, 60, and 64, and when we go up to Uni 3 you're going to see 149, 153, 157, and 161. And if you go into the 5 GHz ISM band, there is an ISM channel there, but that channel is not really used by 802.11 devices. Uni 2 Extended offers 11 more channels there in the center, but again, they're DFS channels, and there may not be any clients in your airspace supporting that. If you enable those channels, you could have access points up and running that never have any clients connect to them. For that reason, as well as the environment and signal strengths required and the applications you're running and the capabilities of the device, you should always remember that when you deploy wireless networks, it's never about deploying what the APs are capable of doing. It's about deploying what the clients need to make the network work properly. This is an example of a channel reuse plan in 5 GHz. Sticking strictly with Uni 1 and Uni 3, you can co-locate 8 access points in the same physical space without being required to use the same channel. When deploying 802.11 networks, it is important to remember that RF signaling is 3-dimensional, not just 2-dimensional. And when you're planning your channels out, you obviously know not to put 2 APs right next to each other on the same channel. But what about above and below those APs? You should also plan cell overlap vertically as well as horizontally. Planning in all 3 dimensions will increase your throughput and increase user satisfaction. Regulatory bodies, and by that I mean governments, control 2 very large things that affect us in 802.11. They control the frequencies on which we are allowed to operate and the amount of power that we are allowed to use within those frequencies. In the USA, it's the FCC. The ISC is Canada, the ERC is for Europe, and the ARIB is for Japan. Every country should have some type of frequency and power regulations in place that you should always respect to avoid being in an illegal state by deploying using too much power or the wrong frequencies. When using Aerohive's Hive APs, you can simply choose the country code and it will lock the access points to the specific frequencies and powers for that region. Thank you for watching this session from Aerohive on an overview of wireless standards, organizations, and fundamentals.